So hi there, this is Avinash, and this is what I did as part of uh, the evaluation part of the course structure. So this is the given data where we had four variables, and then I had to add one more variable for my third model, which I'll explain in the later point. So if we have to identify the PE actual, this is actual data which has been given, and these are the four variables that we already have. Now in the first model, what I did is I took exactly the same data, which means 70, almost 70%, 70 to 75% of the data, which is like 7,500 rows data to train the model. And the first model consisted of all the four variables, and this is how the results yielded. So if you could see the regression table, R square came out to be 92.77, uh, which is uh, which is a good model, but in my third model I found even better solution, and most of the graph plots were good apart from this v variable where I could see some uh, heteroscedasticity. So what I did is I took the predicted p here, and then I found out correlation manually. Then I also did r square manually. Then I had to find VIF. The lesser the VIF, the model is good. So my VIF ranges are from 13 till 15. So and then I found the error, which is actual minus predicted, and whole squared it to arrive at the RMSE, which is the rooted mean square error, which is the metric that I chose to validate the models. So RMSE is like a error metric which tells how much variance we expect from the actual expected output. So if you see the problem statement, the actual output that we were predicting was in the range of 420 to 495 megawatts, and my model is yielding a error range of 456 megawatt, we could say, which is well within the range. So then what I did is, since the uh, volume part, sorry, exhaust vacuum part is impacting my model, in the model 2, I removed the V and then I trained the data. So this time V was not in the game. I only considered these three variables with PE actual as the output dependent variable. Then this is how it came out. It was good. It was almost the same. But the problem is the R square, if you see, the percentage of variance was falling down. I mean, it is coming close to 90. Anything less than 90% we could say is not a good model. Also, p values, not everything is significant. You could see some values are coming out of the significant range. So this model has become even worse than the first model. So then what I had to do is, in the third model I have to take polynomial regression, which is I have to take either of these feature and square it up. So I chose 80 average temperature and squared it up, and this is how the third model came out to be. Now if you could see the difference, all of these more see graphs have a better shape. I mean, when I say better shape, there is no structure as such, which means the model is doing what it has been intended to do. Even the p values are good. R square value has improved. Now this explains most of the variance. All of these p values are significant, which is again a good measure. Now, since I've added the third model, which is the best of all the models that I've trained, now I've kept the 20%, 20 to 25% of the data for testing purposes. So I tested this. This is the test data that I've reserved. Now I tested model 3 on this test data. Now, to my surprise, what it did is the results were even better. the multiple R is 96%, and then the R square is little better than the third actual result, and all the values are significant, which means that this model has even more uh, potential or capability to perform well in the test environment or real world data. So this is how I arrived at the best model out of the all. So to answer the questions that were asked, the type of machine learning approach that I chose is supervised learning. Obviously, we are trying to train the model with existing data, and it finds the target using the historical observations. And the metric that I chose is RMSE. Like I explained, it explains for the prediction accuracy in the total output in megawatts. Then also I used R square manually. I also calculated it is also there in the results to verify the accuracy. Now, what are the features that we have? Like in the question, we have ambient temperature, vacuum pressure, atmospheric pressure, relative humidity, and temperature squared, which I did used in the third model. So these are all the features that I selected. Then how did I split the data? I used almost 75 to 80% of the data for modeling, and then 20% I reserved for testing the third model accuracy. And validation strategy, same thing. I used fixed training set. I have not altered the training set. I only added one more feature of 80 square. That's it. And I've compared all the three models to arrive at a best model. And you could see lesser the RMSE, better it is. So my squared error, root mean squared error, is less in the third model. So I would like to stick with the third model as the best model of the all, with R square of 93.45%. So if I have to model in the equation format, it would be like this, right? I have to multiply the 80 with my result here. Across each of these variables, I will multiply them, sorry, each of these coefficients, I will multiply these coefficients with the predicted PE to arrive at the actual PE. Plus, I will add the uh, intercept, y-intercept. So this is how I've modeled to arrive at the best of the three models that I've tested. Thank you.